Hello and welcome to the Basic Ultrasound course offered by the Philippine Society of Ultrasound for Surgeons. My name is Professor Ricardo Quintos, and I will be talking to you about the basic physics and fundamentals of medical ultrasound. For any ultrasound imaging system, there are major components that are found in all of these systems. So they are broken down into these major components. First is that there is pressure produced by sound that is released and picked up by the transducer, which is then brought into the central processing unit, which processes the data and the signals that are obtained by the transducer. And eventually, these signals are converted into something that can be seen, or that is light energy that can be displayed on a monitor for our analysis. So let's go through them one by one. To discuss pressure, we need to discuss what sound is. In this lecture, we will be talking about the physics of sound energy, the wave properties and their significance, and we will also be talking about ultrasound principles, the ultrasound interactions with tissue, basic ultrasound theory, and the different ultrasound modes. Sound is energy transmitted as a mechanical longitudinal wave that travels in a straight line through a medium. This is the definition of sound that will show you that all of these important components should be present for sound to occur. It is an energy that is transmitted as a mechanical longitudinal wave. It travels in a straight line and it requires a medium. Without any of these different properties, then there is no sound. So it says here that sound as an energy requires the medium through which it will travel in a longitudinal wave in a straight line for the sound to be completed. The different categories of sound are as follows. We first start with audible sound, and this is the reference point, which is the audible to humans kind of sound. And the frequencies that humans are able to hear and detect with their ears is the sound that vibrates from 20 hertz to 20,000 hertz. Below 20 hertz, it is too low for humans to hear, and that is what is categorized as infrasound. Above 20,000 hertz is ultrasound, and that also is beyond the range of human hearing. But many other animals may be able to detect infrasound, such as whales in the ocean, and ultrasound can also be detected or heard by other animals, such as bats and other insects. Now, sound, when it is produced by the vibration of objects, it will be propagated. How will it be propagated through a medium? Sound is propagated when the vibration of the source will cause a compression and rarefaction of the molecules of the medium. The compression regions are the high pressure regions or areas of increased air density, if air is the medium, or increased density of the medium molecules, and that is where we have the compression segments of the propagation of sound. The rarefaction segments are the low pressure regions or areas of decreased air or medium molecular density. So with this decreased density of the molecules of the medium, there is a rarefaction. And if you have a series of condensations and rarefactions, then you will have a wave that is then propagated throughout the medium in a particular direction. Just for academic purposes, there are two types of waves. There are longitudinal waves and transverse waves. Longitudinal waves is that the particle motion is along the direction of the wave energy propagation. For example, in segment A here, the particle motion is along the longitudinal axis, and that is along the direction of the energy propagation. The energy propagation is moved from left to right, and the particle motion is also moved from left to right. That is what is called longitudinal waves, and that is an example of how sound waves are propagated. Transverse waves, on the other hand, is that the motion of the particles is perpendicular to the direction of propagation of the wave energy. For example, here in this diagram, the particle motion goes in an up and down manner, but the waves are produced and the direction of the waves are perpendicular to the motion of the particle. These are also known as shear waves or stress waves. This is not how sound waves move. So sound waves, for our purposes, are only longitudinal waves. Now, when you talk about waves, there are certain characteristics of the waves that you will have to know, which will define the kind of wave that is being propagated. And these properties are these characteristics which describe the wavelength, the frequency, the amplitude, and the acoustic velocity. The wavelength is the distance that one complete cycle occupies. If you have a wave here, one complete cycle is a movement from the top of the wave to the bottom of the wave back to the starting point. So that is one wavelength. If you will imagine it in a static two-dimensional area, that is one cycle because it goes from up, down, and then up again. So that is one cycle. So at a particular point in the wavelength, if you start at the crest or the top of the wave, then you have to end the cycle again at the top of the wave. So that is the distance that one complete cycle occupies. Mathematically, the wavelength is a function of propagation speed and frequency. We will be talking about this later on when we talk about how waves will be traveling through certain media. The second characteristic or the second property of waves is frequency. Frequency is the number of wave cycles that pass a given point per time, and it is defined by the unit hertz. So the number of waves that pass through a given point per given time, like for example, for 1 second, that will determine the frequency of the wave. So if the waves are closely packed together, then there will be more waves per second, and that will make that wave be called a higher frequency wave. Whereas if the waves are longer in duration and there are less waves passing through a particular point at a particular time, then that will be a low frequency wave. So 1 hertz is 1 wave per second. Now, sound will usually go with many frequencies or many waves per second going through a particular point in time. And we can have 1,000 or 1,000,000 hertz going through a particular point in time, and that will be called 1 megahertz. The third property of a wave is called the amplitude. The amplitude is defined as the strength of the sound wave. The strength of the sound wave is basically the difference between the average and the maximum value of an acoustic variable. So you measure the height or the depth of the wave from the baseline, and that is the amplitude. In layman's parlance, that is the strength of the wave or the intensity of the sound, with a higher amplitude resulting in a louder sound. With a smaller amplitude, then you will have a softer sound. Finally, The acoustic velocity is one property of the wave which takes into consideration the characteristics of the medium. Because the acoustic velocity is the speed at which a wave propagates through the particular medium. And this acoustic velocity depends on the acoustic property of the media. It does not depend on the vibration of the particle. It does not depend on the element of the particle that is moving, but it is dependent on the acoustic property of the media that affects the propagation of the wave. So we note here that the acoustic velocity is not the same as the particle velocity. Particle velocity refers to the speed at which the particles vibrate back and forth across their mean positions without any mention of the media or the medium. But the acoustic velocity is the speed at which the wave moves through the medium. And there are many different characteristics of the medium that will affect the wave propagation through it. So basically, the speed of sound, which affects the wavelengths, because we did say that the wavelength is equal to the propagation divided by the frequency. And the speed of sound then is affected by the medium in which it passes. For example, for air, the characteristic velocity of sound is about 330 meters per second. For water, the speed of sound moves faster at 1,480 meters per second. Through fat tissue, it's about 1,460 meters per second. In liver, it is 1,555 meters per second. In the muscle, it's 1,600 meters per second. And note that through bone, the speed of sound quadruples to about 4,080 meters per second. To simplify, the average acoustic velocity in human tissue is about 1,540 meters per second. And this is the value which is inputted into most ultrasound machines in order to make computations as to what the average speed of sound is in human tissue. With that, we have to understand now, with using ultrasound in humans for medical purposes, we have to understand now the interactions of ultrasound with tissue. Certain concepts come into play. The acoustic interface is that which occurs whenever two tissues of different acoustic impedances or acoustic resistances are in contact. So if there are two tissues with two different acoustic properties and they come in contact, there will be an acoustic interface. Even if there is not an anatomic structure there, the ultrasound waves that will be seen, that will be reflected from this contact of two tissues of different acoustic impedances will be seen as an acoustic artifact. And we'll have to understand that these artifacts are sound artifacts and not anatomic artifacts. Acoustic impedance is basically the product of the material's density and the velocity of sound in the material. And it is also a measure of just how much the resistance of the propagation of sound is in that material medium. Here now is a table of the properties of the different media in the body and also in the environment. For air, which has a density of about 1.2 kilograms per cubic meter, the velocity of sound in air is about 330 meters per second, and the resistance or the acoustic impedance of air is very, very low at 0.0004 grams per square centimeter per second. Now, when it comes to water, which has a density 1,000 times more than air, but a velocity of 1,480 meters per second, the acoustic impedance is about 1.48. Now, looking at the tissues, soft tissue average has a density of 1,060, and velocity has an average of 1,540, which has an acoustic impedance of 1.63. Going to bone, the density of bone is about 1,912 kilograms per cubic meters, and the velocity is 4,080 meters per second. And the acoustic impedance is measured in bone. It's a very high resistance, which is about 7.8, compared to the acoustic impedance in soft tissue and compared to the acoustic impedance in bone. You will see that in soft tissue and in bone, the acoustic impedance does not differ significantly. So sometimes you will see ultrasound images of blood and the movement and the propagation speed of the ultrasound through blood and the ultrasound propagation through soft tissue is not going to matter too much. But when it reaches bone, there is a very high impedance to the movement of sound to the bone, such that it has a very high acoustic impedance. And that is why we sometimes see, or we generally see, that ultrasound will not penetrate bone and we will not be able to see the structures that are underneath the bone. So impedance is basically the resistance to sound as it travels through a medium, and it is computed by having the density of the medium multiplied by the speed of sound. Now, since acoustic velocity is dependent on the medium, we have to also understand that different characteristics of the medium will affect how sound propagates through it. Now, the properties of the medium are its elastic properties, its density, its compressibility, and its bulk modulus. The elasticity refers to the ability of an object to return to its original shape and volume after the force is no longer acting on it. The density of the object, or the density of the medium, is the mass of a medium per unit volume. The compressibility of the medium is its ability, or indicates the fractional decrease in volume or the change in volume when pressure is applied to the material. With greater compressibility, there is decreased velocity of sound. With more compressibility, there is increased velocity of sound. The bulk modulus is defined as the negative ratio of stress and strain. Stress is the force per unit area or pressure applied to an object, while strain is the fractional change in volume of the object. So pretty much bulk modulus is the ratio of the force unit or the pressure applied to the object compared to the strain, which is the compressibility of the object.